Get into next part, momentum. Okay. Now again, it is defined like mod psi x comma t, mod psi x comma t whole square dx. So this is equivalent to our rho of x comma t dx. So can I write like this? Again, in case of classical problem, whatever we have discussed, your probability density was independent of time actually, but here it may depend on time in the most general case. Okay, suppose again some states in some states it will be independent of time. We shall see later. Okay, in the next chapter. So that's why rho of x comma t dx. Again, so this is equivalent to this one. This is probability density. This is our probability density. That's why how we found expectation, sorry, average x in case of last classical problems, minus infinity to plus infinity x into rho of x comma t dt. Let me write like this. Let me take most general case where it may depend on time. Dx, sorry, dx, sorry. Is that okay? Dx. So now that is here in case of wave function, since we have interpreted this one as, again, after normalization only you should go for this one, isn't it? After you define this one as a probability, then only you can go for average values, isn't it? Again, you have defined, do you remember, average j is equal to summation over j probability of j. When you define this one as probability, then only you can use this one. Once that definition of probability itself is meaningless, how can you go for that one? This probability definition is meaningful only when total probability is 1. After normalization only come to this step, okay? Otherwise, I'll tell you what to do. If you are not normalized, you have to divide by that psi star psi dx. Some book will give like that. Is that okay? Speak out. Speak out.
Okay, so
if you are not normalizing, you can't use that one to find average value. If rho of x was not normalized, if that probability density was not normalized, then you can't go for, again, how can you use that one as a probability, isn't it? I remember again, so yesterday we have written this one, so probability from a to b, so that's equal to integral a to b rho of x dx, am I right?
Yes.
Then average x integral from minus infinity plus infinity rho of x dx multiplied with x, isn't it? Just like here, like that we did, isn't it? So only when total probability is 1, this should be first condition. If total probability is equal to 1, then only you can do probabilistic interpretation, then only you can use that one for expectation value. Remember properly. Is that okay? Otherwise, you have to divide with integral of rho of x dx, but I don't go for that one. We first normalize, then we better to move on, just like mentioned in Griffiths, okay? Is that okay? So x into mod psi x comma t whole square dx. So this can be function of time. Look at here, very strange. Minus infinity to plus infinity mod psi x comma t whole square dx. This is independent of time, isn't it? This is independent of time.
Yes.
But if you multiply by x and if you integrate, that may be depending on time in the most general case.
What?
I mean, you have to see the examples, then only you can.
So there is no time,
No, again, you are multiplying it. This will become some other function. That time variable may remain in the after integration. That's what I'm saying, okay? Be careful here.
we assuming on
No. This will happen. Again, we shall see. In the next chapter, we shall see many problems. This is derived using Schrodinger equation, but there is nothing to say that this is independent of time. This may be depending on time. After you integrate with respect to x, what would happen? This time variable remain. X variable will go, isn't it? Here also, but here, so time variable will also not remain in this situation. Okay, this is derived one. Are you getting my point? There is no derivation for that. This is independent of time. Okay, yes. Now look at here. I hope you got how to use this wave function and interpretation to find average value. Is that okay? Because mod psi square plays the same role as rho of x as we did in the yesterday's discussion.
Yes.
Is that okay?
Yes, sir.
So mod psi square into dx, that is nothing but rho of x into dx multiplied by x. This is the way of calculating average value in case of statistical part, isn't it? If you define probability. But remember, so first ensure this condition. What is this one? Minus infinity to plus infinity mod psi square dx is equal to 1. Then only come to this one. Otherwise, it will be meaningless. Because that definition assumes that this is a probability, isn't it? This is probability density, this is a probability. This can be probability density, this can be probability only when it is normalized. Only when total probability equal to 1. Is that okay? In case of classical system, whatever we have taken, it happened naturally, okay? But here it will not. Otherwise, there are other ways. Suppose if it is not normalized, we can do like that integral minus infinity to plus infinity x into mod psi square dx whole divided by you divide with that term. You may find this one also in some textbook, okay? If it is not normalized, we should go for this definition. Okay, in case of statistical physics, we use this kind of definition while finding average value. You shall see, okay? Now, what is the difference between, so this one and our classical average value? This is also average. There also we found average, am I right? In case of classical part, isn't it? What is the difference? The difference is, look at here. So to find this average experimentally, you can't take same system. We have taken one ball, am I right, which was falling. We have taken millions of photographs. We have done repeated measurement on the same ball, isn't it? Or you can once it falls the ground, again you can keep the ball above and you can leave that one. You can do the repeated measurement on the same system, isn't it? So in case of harmonic oscillator also, suppose a mass which is attached to spring, you can do repeated measurement. You can take any number of photographs with a flash, isn't it? System is not disturbed. Okay, so there the average you can do the experiment. Suppose if you want to verify the average values, you can do the experiment on the same system. You can do the observation on the same system. You can do the repeated measurement on the same system in case of classical system. But here we are talking about microscopic system, small particle, quantum system. Each of our measurement is disturbing the system. Okay, to define this quantum mechanical average x, am I right? Average position.
I pass on one. Expectation of x and average of x is same.
No, expectation is the word used in quantum mechanics. Here also we say average sometimes. We say average as well as expectation. Both words are used.
Can you distinguish between them?
No. Again, that is just word. That's just a word. In classical physics, we don't say expectation value. In quantum mechanics, we say expectation value. Sometimes in quantum mechanics also, we say average value. That's what I'm saying.
Okay.
Average value, we say both in classical as well as quantum. Expectation value, that word is only for quantum. Expectation value is the better word actually in case of quantum mechanics. Is that okay? Rather than average value. Okay? Wait a second. Let me explain that one. Yes. Yes, speaker.
Like the average value, there is no need that expectation value one of the given value.
Yeah, wait a second. I'll come to that one. I'll come to that point. Wait a
One question
second.
is there actually, sir.
Huh.
One question is there in that book. Expectation value is different.
Yeah, again, expectation value need not be what you call any of the measured value, isn't it?
Yes.
Expectation value may be different. We shall come to that point. Wait a second. What I'm saying here is, wait a second. This expectation value, again, you are thinking a little bit ahead. This can be depending on time. Oh, no. What I'm thinking is, again, how do you experimentally see this expectation value, average value in quantum mechanics? You should take identically prepared system. You should do the measurement. Then you take the average. I told you, isn't it? Suppose if you have a what you call system with this wave function, okay? Mod psi square is like this, okay? So now you need to find average x. Experimentally, you need to find average x. Now you should take identically prepared system, millions of identically prepared system. We say ensemble of identically prepared system. Okay? Like this. You should take ensemble of identically prepared system. You should do the measurement on each. You should find what is the value of x you get, then you take average of that one. Is that okay? Then you take average of that one. That is this average. Is that okay? Quantum mechanical expectation value is not similar to classical average. Okay. So this is, he'll write that one. Expectation value is the average of the measurement done on the ensemble of identically prepared system. That's very, very important distinction. Okay. How do you, again, I found this one. I'll write some value now. How do you verify that one? While verifying, don't do the measurement on the same system, because each measurement is disturbing the system. You should take identically prepared system. All of they are in the same state. Is that okay? So like this.
Sir, here expectation value nothing to do with the most probable value.
No. Expectation, that is again, expectation value may be equal to most probable value in case of symmetric distribution. Are you getting it? I mean, I told, isn't it? Average and most probable, again, that is, some parts are same, but interpretation is different. That's what I'm saying. Again, that probability idea is same. Is that okay? Probability distribution, those ideas are same. That mathematics is same, but interpretation is different. Okay, that's why we renamed. We haven't called it as average. Sometimes we call it as average also. That's what I'm saying. But so we call this one as expectation value. We call this one as expectation value. That expectation value, again, if you do next measurement, that doesn't mean you will get this value.
Yes.
Are you getting my point? You get, suppose, in case of earlier problem, you got expectation value as x equal to a, isn't it?
Yes.
That doesn't mean next measurement, if you do position measurement, you will get a. What is the expectation value? Average of the measurement done on the identically prepared system. Why identically prepared system? Each measurement is disturbing the system. We should do the measurement on freshly prepared system. Then only that interpretation is correct. Is that okay? Yes.
So that's why the time derivative will be not zero.
No. That is the quantum mechanical property. Again, in the most general case. Is that okay? Why the time comes here? Again, so look at here. There we have taken rho which is not a function of t, rho of x only in case of classical questions. Okay. Here again, this is the most general case. Psi as a function of time also, where mod psi square is defined as probability density. Then when you do this integral, it may be time dependent. In the most general case, you better to say it is time dependent. Okay. So again, I'll come to the time dependency later. Okay. What I'm saying is, how do you explain this one? How do you experimentally verify this one once you calculate this one? Okay. So that should be done like this. Yes.
So they are written not the average of repeating and the same system means.
Yeah, it is not average of the measurement done on the same system, because first measurement itself disturbs the system. Second measurement you are doing on the disturbed system, not on the freshly prepared system. Are you getting my point? Is that okay?
No, sir, I do not understand the meaning.
No. Again, have you heard yesterday's lecture completely?
Yes, sir.
First measurement, will collapse. Again, look at it. I have taken only one system. Okay. First measurement will collapse the wave function like this. Okay. At C. Okay. X equal to C. Second measurement on the same system, it will give C only. It will give C only. Third measurement, it will give C only. Average will be C only.
Yes.
Are you getting my point? That is not the way that we need to do.
Yes.
Is that okay? See again, this is not how we experimentally calculate this average or experimentally verify this average. Are you getting my point? C may be some less probable case, but maybe in the first observation you might have found that one. Are you getting my point? Each of our measurement is disturbing the system. That's why you have to take identically prepared system. You should do the measurement on each. Then you should take the outcome, measurement outcome. Those are position. Then you have to take the average of that one. It's just like, again, tossing one coin again and again. That's again, definitely that will give the answer, because tossing the coin will not change the shape of the coin, isn't it?
Yes.
So suppose if each toss, after the toss, suppose if something would happen to coin, let me assume like that, then what I should do? I should take millions of coin, I should toss them together. to verify probability being head and tail equal to half and half, isn't it? Is that okay? But we don't do that one. We toss single coin again and again to verify, isn't it? That's okay with classical system. Suppose if coin were quantum system, suppose each toss was disturbing the next measurement.
Yes.
Once you toss the coin, you got head, okay? Next measurement was very fresh over there, isn't it?
Yes.
No, but here it will not happen because you are hitting that one with a photon. You are disturbing the system. Is that okay? You are talking about quantum system here, small system here. Your observation is disturbing the system. Tossing one coin 100 times is equal to tossing 100 coins once. You know this one, this concept from probability? Yeah.
Equivalent.
We choose second one because each of our measurement is disturbing the system. Is that clear now?
Means for each position, we are having a pressure system for calculation of number of particles or number of samples.
Wait. For each?
For each measurement, for each position, how many numbers of particles are? So we have a number of pressure repair system for each position.
I have only one particle, okay? I'm talking about one particle state here, okay? I have one particle state, but to verify that one, I have millions of particles which are all prepared in the same state, okay?
That is the important thing.
Millions of particles all are prepared in the same state, psi. Is that okay? Now that number you are talking about, that number of particle versus x, okay? How many number you got at this point? How many number you got this point? That will give this distribution. If suppose your mod psi square is like this, okay? That will give you this distribution. That is different. Verifying distribution I told yesterday, isn't it? I told the same thing.
Yes.
To verify distribution also you should take millions of system and you should do the measurement, okay? So then what will happen? So in the more number of cases you get position here, more number of identically prepared system which will give the position answer here, less number of system will give the position here, isn't it? Yesterday I think I did the same interpretation.
Interpretation, okay, but how do I prove this mathematically? This wave function is summation of all these wave functions?
No, that is later. That mathematics is later. It is a combination of different position states. That mathematics is later. Hold on. Now I am talking about how to, you say something, am I right? How to verify? You say this is probability distribution. How do you verify? Take millions of identically prepared system, do the measurement so that this is number of system with position x as a function of x. You can't make it continuous, okay? Because here you should do a kind of histogram. That histogram exactly looks like this. Is that okay? So similarly, to verify this average value or expectation value of position, in quantum mechanics, you should go for identically prepared system, millions of identically prepared system, or we say ensemble of identically prepared system. You should do the measurement on each. You should take that x value and then you should take the average. Is that clear? So that difference you need to find out, okay? Expectation value is the average of the measurement done on the identically prepared system, not average repeated measurement on the same system, because it will disturb the system. Is that okay? Next coin, if that coin shape is changed after one trial, next one may not be probability of being head and tail are equal, isn't it, in that case?
So once
If coin shape is changed.
sorry.
Yeah.
Once collapsed by photon, hit by photon of the observation, we will stop that observation?
No, whether you stop or not, again, you stop, you leave the system. That system is over.
Vanish.
Yeah, not vanish. Its part is over. Okay, its role is over. Once you do measurement, I'm talking about identically prepared system, isn't it? Once you do measurement on system, its role is over.
Then
Okay, then you can't do repeated measurement to talk about mod psi square or average value.
Then,
Okay?
Then
You
sir, we can think about this quantum particle classically. That's why.
That is the case. It is not classical particle. Our observation is disturbing the system.
Okay.
Is that okay? So that's why you should take identically prepared system and you should do the measurement to verify any of these ideas. Are you getting my point? Any of quantum idea, you should take identically prepared system, then you should do the measurement, because your measurement is disturbing the system. If you keep on doing the measurement on disturbed system, you can't verify any of this idea. That's why we call this as expectation value. Okay, that means what you call average of the measurement done on the ensemble of identically prepared system. Is that clear? Quickly. Now, so next idea here is this can be time dependent also, isn't it? In the most general case, this can be time dependent also. That's what I'm saying. So then take dx by dt. We shall see what would happen. Okay. So that means this is equal to d by dt of integral minus infinity to plus infinity x into mod. Let me write mod psi square. Okay. I'll not write x comma t, but you just assume like it. Okay. Dx here. Okay. Now look at here. It is total derivative. Am I right? I hope you know what is the total derivative, partial derivative. Now, once you integrate with respect to x, this x variable will go. Only time variable will remain. This whole integral, after integration, this is a function of time alone. Single variable function. Are you getting my point? No, you are not listening. After I integrate with respect to x, that x variable will not remain. You are going to integrate and then you are going to put the limit, isn't it?
Yes, yes.
What variable will remain? Time variable will remain. Isn't it? That time again, that means this whole thing is a single variable function. Time, it depends only on time. If it depends, it should depend only on time. Since it is a single variable function, I have written total derivative. Okay. If you want to take this one inside the integral, it will become partial derivative. So what will happen is d expectation x by dt.
Sir, how that t variable remained, I didn't understand.
Sine x into t. Integral sum 0 to a dx. Do this integral where t is time. Again, you are doing integration with respect to x here. Time will remain here, isn't it? Are you getting a point? Or just make it simple. 0 to a sine xt dx. You have two variables here, but you are integrating only with respect to one variable. What is the answer?
Okay, sir.
Minus
Okay, sir.
cos xt minus cos xt. Okay. Divided by t 0 to a, isn't it? It's a time dependent now. That's what I'm saying. Okay. Now what will happen if you want? That's why I have written total derivative. Total derivative you write only when it's a single variable function. That variable is only time variable here. After integration, only time can be the variable part. Okay. Now look at here. When I take that one inside the integral, this would happen. Dou by dou t of x into mod psi square dx. Calculus will allow us to do so. Is that okay? Because now inside one, this is a function of x, this is a function of x as well as t. Two variable function.
Sir, it is cut it on the screen, sir. Above part, sir.
Okay. Is that okay?
Yeah.
Mod psi square dx. Because now it is two variable function. Partial derivative. You should take partial derivative. When you take partial derivative, when you take derivative of two variable function, you should go for partial derivative, isn't it? Now look at here. This can be taken inside, okay, like this. Integral minus infinity to plus infinity. So x you can take outside because partial derivative. I hope you know something. So dou by dou t of, look at here. This psi star, I'll write it as mod psi square, I'll write it as psi star into psi dx. This is d expectation x by dt. Quickly, I'll just move on quickly because I want to finish out this concept. Okay, time 8:30. Now, So this one I'm going to elaborate. What is this one? Again, so in case of differentiation, you can write it as, look at here, dou by dou t of psi star psi, that's equal to psi star into dou psi by dou t plus psi into dou psi star by dou t, isn't it? Can I write like this? Differentiation, UV formula. Differentiation, UV formula. Now look at here. What I do here is I'll take Schrodinger equation. IH bar dou psi by dou t. This should be capital psi, okay? But anyway, so that's equal to minus h bar square by 2m dou square psi by dou x square plus v of psi. Is that okay? I take complex conjugate of whole equation. Minus IH bar dou psi star by dou t, that's equal to minus h bar square by 2m dou square by dou x square of psi star plus v is a real function. So real, this is v is real, it's a potential, scalar potential. It will never be complex. Potential. Function of position usually. Function of position in case of so conservative system. It will never be complex. So v as it is. Psi star. Is that okay? Now I will multiply this one with psi star. I'll multiply this equation with psi star. I'll multiply second equation with psi. And I will subtract one from other so that this part will be cancelled. V psi psi star. V psi v psi star. Okay. Usually v is a function of x comma t. You can take it anywhere. This is not any operator of like derivative kind of operator. Is that okay? V contains x. X is not any derivative operator. I think I told about. Yeah, v is real. V is real. Again, you may think like v cap is here, isn't it? Operator. It should be operator, isn't it? So that doesn't matter. You can interchange that one. We shall see that one later. Okay, you will understand again what kind of v that we are talking about. Okay. Now look at here. Now once you subtract that one after multiplication, this part will be cancelled. Can you imagine? So that this will be IH bar psi star dou psi by dou t plus subtracting. Okay. Psi dou psi star by dou t, okay, psi dou psi star by dou t. So that is equal to minus h bar square by 2m, okay, psi star dou square psi by dou x square plus psi dou square psi star by dou x square. So tell me if I am wrong anywhere, okay. Is that okay? Wait. You are subtracting. Okay. This one into this one minus this one. Am I right? Minus this one. You should get negative sign here. Be careful. But here if you subtract, you get positive sign. Now what is this one? This is nothing but this one. IH bar multiplied. Is that okay? So then what I do here is I'll take this IH bar here. Okay, dou by dou t of psi star into psi, am I right? This part. So IH bar, I'll take it here, minus h bar square by 2m, one of the h bar got cancelled, 2I into m. Can I write like this? I will come to denominator, one of the h bar got cancelled here, okay? Multiplied with psi star dou square psi by dou x square minus psi dou square psi star by dou x square. Let me try to do it very quickly, okay? X into, look at here, x into, can I take that h bar minus h bar by 2 I am outside? minus h bar by 2im, I'll take it outside, okay? So integral minus infinity plus infinity x into, okay, psi star dou square psi by dou x square minus psi dou square psi star by dou x square, okay, dx. Now I'll do integration by parts. I'll take it here because it takes more space here, okay? I have used Schrodinger equation, remember, it's all property of Schrodinger equation. It is giving us these kind of ideas, okay? Now, what I do here is now d expectation x by dt, okay, that is equal to, look at here, minus h bar by 2im, okay? Now I'll do integration by parts, but before that one I'll do one more step here, okay? Before that one, that step, look at here, I got some practice, that's why I'm writing like this, but you have to think in a reverse way to understand this one, okay? X into, this whole thing can be written like this, dou by dou x of psi star dou psi by dou x minus psi dou psi star by dou x into dx. If you do this one, what will happen? Here you will get 2 term, here you will get 2 term, total you will get 4 term. Among them, 2 term will get cancelled, 2 term will remain actually. You should do that one. This is second derivative, isn't it? So again, if I do this one, you will get this one. So check it out later. Okay? So check this out later. Now, first function and derivative of some other, isn't it? I'll take this one as second function. I'll do integration by parts. Okay? What is that integration by parts? So first function, or I'll put a flower bracket. Okay? First function into integration of second function. Integration of this whole thing is second function. Okay? And you should substitute to the limit, isn't it? Minus, look at here, this bracket I will close it later. This bracket is quite important, okay? Minus integration of second function, that means inside part, okay? Psi star dou psi by dou x minus psi dou psi star by dou x into differentiation of first function, that is 1 dx. Now I'll close this flower bracket. Is that okay? Quickly. Now what will happen is, look at here, at plus infinity as well as at minus infinity, this is quite dominating term, and this will be 0 because we are taking normalizable solution. We have taken normalized wave function, am I right? Yes. Normalized wave function can happen only for normalizable wave function. Simply. Is that okay? So now, so look at here. So this even though you have x here, so this is quite dominating. You will understand later. It will be kind of exponential, that kind of thing actually. Okay? So then it will be dominating. What will happen is at plus infinity as well as at minus infinity, it will take the whole term to 0. So that's why this part is 0. Is that okay? Or if you take any finite region, at the end of the region, your wave functions are 0 actually. We shall see. Suppose if you take particle in a box. In that case, x will not become infinity. Only problem you may think of here, yeah, this at plus infinity, x also can be infinity, isn't it? Maybe this may be 0, wave function may be 0. Is that okay? But the x will be infinity. No, this wave function part will be dominating. It will be a kind of exponential function many times. Look at here. You should plot this one. Okay. E power minus x square. Okay. What will happen? It will go to 0 as x tends to plus or minus infinity. So what is x into e power minus x square? So plot this one. X into e power minus x square. Is that okay? X square into e power minus x square. So plot this one. Even though you have x square which goes to infinity as x tends to infinity, this is dominating term. It will drag that one to 0 actually. So plot these three, you will understand. This kind of situation will happen. That's what I'm saying here. This kind of situation will happen here. Kind of situation. So that's why that term is 0. Is that okay? That term is 0. Now, I got one term that is remained. Again, negative sign, so that h bar by 2im, isn't it? Now what I do is, I'll keep this one as it is. I'll do integration by parts of second term. Yeah, anyway. So I'll do partial differentiation of this, not partial differentiation. What is that? Integration by parts of second term, okay? So that minus infinity to plus infinity, psi star dou psi by dou x into dx, okay? First term. First term. This minus I have taken here, isn't it? This minus will remain. Minus, I'll do partial, I'll do integration by parts, minus, what will happen? Integration of minus infinity to plus infinity. I'll write one more step. Psi into dou psi star by dou x into dx, okay? I'll do integration by parts here. H bar by 2im, look at here, minus infinity to plus infinity, psi star dou psi by dou x dx, okay? First term. So in that one, look at here, I'll put it into bracket again. First function into integration of second function. I'll take this derivative as a second function. So psi into psi star running from minus infinity to plus infinity. Minus integration of second function. What is that? Psi star into differentiation of first function. Dou psi by dou x into dx. Look at this one carefully. Look at this one carefully. Again, this is 0. At plus infinity as well as minus infinity, normalizable wave function goes to 0. I told you earlier, isn't it? This is 0 again. So this minus minus plus will happen. Wait a second, I have to close that flower bracket. I have to close this flower bracket so that, look at here, d expectation x by dt, look at here, this is twice, the same integral appeared here, negative negative positive will happen, okay? Same integral will appear here, so that is twice of the one of the integral, so that 2 will get cancelled, okay? H bar by I into m, okay? Integral minus infinity to plus infinity, psi star dou psi by dou x into dx. Is that okay? What I do here is I'm going to multiply with mass. I'm going to multiply with mass. Again, you can call this one as actually expectation value of velocity actually, because we are discussing non-relativistic theory, isn't it? This is a definition, okay? Here comes the definition. You do it later. It's not a big deal. Yes. So again, it's a kind of what you call definition. I call this one as expectation value of velocity. This is a definition.
Velocity, right?
Expectation value of velocity. Speed.
Speed.
In case of one dimension, velocity is speed. Is that okay? Yeah. So now I multiply with mass. And I call that as expectation value of momentum, which is the most general term, isn't it? And when you multiply with mass, look at here. Again, I'll take I into numerator by multiplying and dividing by I.
Yes.
If I goes to numerator, it will become minus I. Minus I h bar integral minus infinity to plus infinity psi star dou psi by dou x into dx. We call this as expectation value of momentum or average momentum sometimes, okay? Minus infinity to plus infinity psi star, look at here, I'm trying to rewrite this one, minus I h bar dou by dou x of. Okay. Now what I do here is, so I'm going to treat this one as an operator. Dou by dou x is a kind of operator. Am I right? You are doing some operation. What is the operation? Take derivative. This whole thing I'm going to imagine kind of operator, which is doing some operation on the wave function that it is operating on. Is that okay? So that's why what I'm going to say is I'm going to call this as momentum operator, because that operator gave me average momentum value, expectation value of momentum. I'm going to define momentum operator P cap, that's equal to IH bar dou by dou x. It's a kind of operation.
So the difference is the kind of operation.
Operation, you do something, am I right? You have some instruction over there. Again, what does operator say? Operator instruct you to do something. What does this operator is saying? This operator is instructing you to take derivative and then multiply by minus IH bar. It is instructing you like that actually. Yeah, speak out.
There should be a negative set.
Yeah, here. P cap. Don't hesitate, okay? Don't hesitate if any mistakes happen on it, okay? Minus IH bar dou by dou x. It's a kind of instruction. That means you take derivative of the function on which you are operating and then you multiply by minus IH bar. That's an instruction. Operator is an instruction. It does some operation on the function that you are operating on, okay? Now look at here. Why I called this one as momentum operator? Because it gave what you call momentum average value or momentum expectation value, isn't it? Now, after seeing this momentum, okay, now look at here. What I'm going to do is expectation P, I'm going to write it like this, integral minus infinity to plus infinity. So psi star P cap psi dx. Actually, this is Px actually. In case of one dimension, sometimes we don't write that one, okay? Is that okay? Now look at here. After I saw this expectation expression, okay, I got motivated to edit this expression. What is this one? X into mod psi x comma t whole square dx, am I right? Now I'm going to edit this expression. Minus infinity to plus infinity. So psi star, because x can be taken anywhere, am I right? X into psi dx, okay? Now what I do is minus infinity to plus infinity. So psi star x cap psi dx, but here x cap is x itself. Operating this x cap operator is nothing but multiplying by variable x. Operating p cap operator is nothing but taking derivative. Operating x cap operator is nothing but multiplying by x. You should do some operation. What is that operation? You should multiply by x. You should multiply by x from here to here. Go from here to here. What do you mean by operating x cap operator? Multiply by x. Is that okay? Now I'm going to rewrite this expression like this. Is that okay? Now I got a kind of style of writing expectation value. Isn't it?
We are saying right now expectation, not average.
But expectation, why I'm saying, because in exam sometimes they say average. You should not get confusion. Okay? In quantum mechanics, we say both expectation as well as average. In classical physics, we use only average word. Okay? In quantum mechanics, we use both words. Is that okay? Yeah. Expectation value. You say expectation value because that is the more better word actually. Because because wait a second. Because in quantum mechanics, you can expect something, but you will not get that one. You can expect something, but if you do the measurement, something else may see. You may see something else, isn't it? Yes, speak up.
Sir, here we are dealing with normalized wave function always.
Yeah. Again, these things, if you do with non-normalizable wave function, meaningless. If you do this one with without normalizing wave function, meaningless. Then again, if you are taking non-normalizable function or non-normalized function, you should divide by psi star psi integral again. Okay, that's what some other textbook mentioned. But Griffiths, he will first instruct you to do normalization, then proceed with any average value, because then only that is meaningful. We have started from here, we got here, and we got a way of finding expectation value for any observable, for any operator. Okay, now look at here. You got one is momentum operator, one is position operator. Am I right? X cap and px cap. Any other observable means position is observable, momentum is observable, kinetic energy is observable, potential energy is observable, total energy is observable, angular momentum is observable. Is that okay? So now, once you define position and momentum operator, which is more general, you will understand this one in Hamiltonian mechanics. Okay? Once you define position and momentum, you can write any other observable in terms of position and momentum. Is that okay? Kinetic energy, p square by 2m. So potential energy in terms of x, isn't it? Angular momentum, r cross p, in case of 3 dimension, not 1 dimension. Okay? Again, r cross p, r means x, y, z, p means px, py, pz. Once you define position and momentum operator, you can generate any other operator using that one. That's why, suppose if you need expectation value of kinetic energy. So now, what is kinetic energy in classical physics is just p square by 2m, am I right? Now, this is the classical expression. If you write variable. Okay? If you put operator, that's a quantum mechanical expression. Quantum mechanically, you don't have any variable. You don't have position variable, position as a function of t. You can only talk about expectation value of position. You can only talk about expectation value of momentum. You don't have that variable. But that is represented by operator. What is the role of operator? It will help you to find these things. Is that okay? What is the role of operator? It will help you to find that average value or expectation values. Okay? Yeah, speak out.
So, sir, sandwiching that operator in some wave function, then that wave function.
Wait. I'll come to that. Now, if you need expectation t cap, then what I do is just I copy the same method. Minus infinity to plus infinity, psi star into t cap psi dx. Where t cap is p cap square. What is p cap square by 2m? P cap operator operated twice. So this will happen to be minus h bar square by 2m into dou square by dou x. We have seen this one, isn't it, earlier? I have defined Hamiltonian. So again like that, okay, you should do like this. Minus infinity to plus infinity, psi star minus h bar square by 2m, okay, dou square by dou x square of psi dx. You should do like this. This is expectation t cap. Similarly, expectation v cap, you can do in the similar manner. Sandwiching this operator, that operator between psi star and psi, and then integrating. So that's a kind of style, or that's a kind of tradition here. Or I mean, that is how you do actually, not tradition or something. Tradition can be changed, isn't it? Is that okay? To find now look at here. I'm going to okay, because the same thing is true for expectation value of Hamiltonian also. Minus infinity to plus infinity. Hamiltonian can also be written in terms of x and p, isn't it? Psi star h cap psi dx. The same thing is true for any general operator. He is going to write like this. Any general operator can be written in terms of x cap and px cap. In case of 1 dimension, sandwich that operator between psi star and psi and then integrate. That is the way of doing expectation value in quantum mechanics. And we say these are the operator represents the variable. You better write down px cap, x cap, t cap. These are the operator represents the observable. They represent observable. They are not observable. No, again, classically, this is a variable. That itself is observable. Kinetic energy variable as a function of t. Position as a function of t. That's a variable, isn't it? That itself can be observed, isn't it? In case of classical mechanics, you can measure kinetic energy, you can measure position, you can measure momentum, isn't it? Now, so operator is representation of that one, not it is not observable. Operator represents observable. Can you write that down? Operator represents observables. Operator represents observable. It is not. It will not give you any variable part. Okay, it will represent observable, and it will help you to give it will help you to find out expectation values. Operator represents observable, or observables are represented by operators. Yeah, that's the best word. Observables are represented by operators. I don't know what he is going to write. Wait a second.
Observables are represented by
Both are same sentence. Am I right?
Yes.
Operator represents observable. Observables are represented by operator.
That is good.
Yeah, English. Operators are represented by. No. Observables are represented by operators, or operator represents observable. Operator itself is not. It will not give you any function or something. Okay, it's some instruction.
Sir, you have written expectation value of operator T or observable?
Sometimes we put cap, or sometimes we don't put here. Anyway, this is one real value. This is always real. This is always real.
So real means classically it's also real.
Classically also real. I mean, what I'm saying is here wave function may be complex. Am I right? You may think like some complex quantity will remain. Isn't it? That will never happen. Is that okay? You may think like that. Look at here. In this case, okay. It was there here. X is equal to minus infinity to plus infinity. X into mod psi square dx. Here there is no issue, isn't it? Even though psi is complex, mod square is real and positive. Again, you don't have any issue. But when you come here, when you come here, isn't it? You may think like whether that any complex part remains after integration. You may think like no, it will never happen. Okay, you will see later. These are all real quantities. Sometimes we put cap here, sometimes we don't put cap. Look at here. He also, I think, no, he don't put cap there. Okay, he don't put cap there. Let me also remove cap. But you should not think that is classical. Let it be, whatever. Okay. Sometimes we put cap, sometimes not. Again, check other book. This is one more theorem that you need to. You may have two different states, psi 1 and psi 2. Two different states or two different solution of Schrodinger equation. Okay. So psi star into psi 2 dx integral from minus infinity to plus infinity. Minus infinity to plus infinity means integral over our region of interest. Okay. Particle in a box, you integrate from 0 to a actually. Okay. So this whole thing is also independent of time. We call this as inner product. Later we shall see. We call this as inner product. That's also independent of time. Just like normalization. But here I have taken two different things. Two different states. Earlier I have taken psi star into psi. D by dt equal to 0. Now I have taken two different states. Psi 1, psi 2. Two different solution of same Schrodinger equation. Normalizable. Yeah. He mentioned that one. Any two normalizable solution where psi 1 and psi 2 are any two normalizable solution. Yeah, he mentions that. This is problem number 1.15. No need to prove, okay? You just remember the statement. That's very important, okay? So operator is a function. No, operator is not function. That's what I'm trying to convince. Operator, by the word itself says operation. It will do some operation. Look at that one. Look at x cap operator. So px cap operator minus I h bar dou by dou x. Am I right? So t cap operator minus h bar square by 2m dou square by dou x square. What is this one? These are not functions, okay? They are instruction to do something. Operators. They do some operation. Is that okay? And give you some information like expectation value. Again, expectation value definition. What is the definition? Average of the measurement done on the identically prepared system. Don't forget.
Sir, if I will take 2 dimensions, then
Dou square by dou x square, dou square by dou y square. So p x cap you define, p y cap you define, dou by dou y minus I h bar dou by dou y.
then derivative will be, I mean, differential will be.
No, this is most general. This is even true for 3 dimension. You can generalize this one to 3 dimension, no doubt. This theorem you can generalize that one to 3 dimension because property of Schrodinger equation, I think. Okay, I didn't see the proof. Property of Schrodinger equation. Is that okay? These are also linear operator. Okay, they are saying that operator are linear mapping. These are also linear mapping only, but these things operates on the function. We shall see linear algebra later. Okay, in the 3rd chapter. That's correct. Okay, operators are linear mapping. I mean, linear operators are linear mapping. Okay, non-linear operator may also be there. We don't use non-linear operator here. These are all linear operators. We shall see what is that linearity property. Okay. Here, whether you put normalizable function or normalized function, the same is true. Okay. Normalization is nothing but one multiplying with constant, isn't it? That constant can be taken outside. That's why it should be normalizable function. That's it. After normalization you do, before normalization you do, you get the same. But these average value do only after normalization. Otherwise, those are meaningless. Okay. And these are, remember, real values. That they will never be complex. No, what I'm saying is you can take a complex conjugate or Hermitian conjugate or something. You can lift this one. You can operate this one on this one, and then also you can multiply by side. That's also true. We call them as Hermitian operator property. You shall see in the 3rd chapter. Is that okay? What he's saying is, why can't we interchange these two? Isn't it? That is possible. But in that case, what we have to do is, we should not just interchange their place. We have to do it like this. Okay, we have to do it like this. We should minus infinity to plus infinity. We should operate this first on psi, then we have to take star, then we have to psi dx. You should do like that. Okay, we shall see this one in the next chapter actually. So this is actually Hermitian conjugate of this one, but Hermitian conjugate is itself, we call that one as Hermitian operator. Okay, we shall see later. All observables are Hermitian operator. Okay, yes, and that Hermitian operator gives expectation value real. This kind of theorem will come that will boost up this one. Now you can't imagine that whether it is real or complex. Am I right? You may think like it is a complex. No, it's a theorem in linear algebra. Expectation value of any observable Hermitian operator is always real. Is that okay? That kind of theorem will come there. Is that okay? So that's why to find expectation value of any observable, okay, that observable will be represented by some operator. Okay, just sandwich that operator between psi star and psi. If you want to find expectation value in some state psi, okay, sandwich that operator between psi star and psi and integrate, and operate this one on second member first, and then multiply by psi star and then integrate. This is the idea. Okay.